So in this video, I'm going to make a start on grade 12 advanced practice questions for the end of term 2 exam. Let's dive straight in. Looking at this here, it's asking me to find the flux from a maximum to a minimum. Maximum flux, remember, is the number of lines being caught by the area. I am catching as many field lines as I can. So if my face is perpendicular to the area like this, I am catching as many lines as I can. Yes, technically this is negative, this is positive, but they're still catching the same number of lines. So the highest flux is like this when they are covering more lines. That means my answer must be B or D. C and A are out. A is equal to B. And then after that, you can see that D is at an angle, so it's catching less lines. Not as many as this, but definitely more than C. So A is equal to B, greater than D, and greater than C. In actual fact, C isn't catching anything at all. C is completely flat. All the field lines are passing across it. So that means the best answer must be D. Greatest, medium, and then the weakest is there. Next here, we're trying to find the average rate of change of flux, the rate of change. So the rate of anything means divide by time, and there's a time here. You'll just divide by time. Anytime you see a rate of whatever, you divide it by time. Rate of change of flux, the change of flux divided by time. So if I want to find this rate, I will take my final minus initial, and I'm going to divide that by my time. So my final, which I have, is 0.20 minus 0.50. And then I'm going to divide that by the time of 2 seconds. Sticking that into the calculator, I'm getting negative 0.15. So directly, I will pick my answer here. However, just a side note, if it asks you for the induced EMF, if it asks you for this, thanks to Lenz's law, the induced EMF is in the opposite direction. If I asked for an induced EMF, this says minus 0.15, the EMF would be positive 0.15. Just in case it asks you that in the exam. If I had a positive answer and I asked for the induced EMF, you pick the negative answer. Because if you remember the formula, negative in flux over time, remember that? There's a minus in this equation. So if you ever asked about induced EMF, whatever number you solve, just don't forget there should be a minus there. Anyway, we'll get to that when it comes. This question is going to be quite difficult to do on this laptop, but I'm going to give it a try anyway. First thing I'm going to do is I can see that I have a north and a south, so I'm just going to put this north to south like this. My magnetic field is pointing downwards. I have a current, or I have a wire pointing out of the page towards me. Okay. It says the wire is moved, a force is applied, and the current is induced upwards out of the paper. So that's kind of confusing. It says upwards out of the paper. It means that it's coming out of the paper. Up as if you're looking at the paper from on top. So if this is your desk right now and you're standing at your desk, you're looking at the desk like this. You're looking at the desk and you're watching the current come up out of the paper like this. This is the wire sticking up. So you're looking at the top of the wire. So you're looking at the top of the wire. This is my two magnets like this, and these are my eyes. I am looking like this, and it's coming up out of the paper. I hope that makes sense. This is supposed to be a table. So if that is happening, I have to now figure out the direction. The wire was moved. All right, fine. So I'm going to ignore my horrible drawing and get started with this. If this is happening, first I need to set my hand up in the way that I have my index finger. This is the right hand rule I'm doing. This is for my students, the right hand rule. I know some of you have used Fleming's left hand rule for this, which is also fine. You do it your way. But for my students, I use the right hand rule. I'm pointing my index finger towards me. If you have forgotten what each one is, I'll quickly recap it. I've done a few videos on this already. So this is my field, this is my force, and this is my direction of my current. The left-hand rule is different. It's FBI. I'm not interested in that. I am going to continue with this. I am pointing this B towards me as if I'm pointing a gun at myself. I'm shooting at myself, basically. So if I'm standing here, I'm pointing my finger to myself. If I'm doing that, my thumb is pointing up, my B is pointing towards me, and my middle finger is pointing to the right. This is how I have aligned myself. My thumb is the wire, which is upwards towards my face. So I am now, again, looking over the desk at my hand. So now I am just pointing at myself with my hand like this, like with a gun. So this is what I'm doing right now. Once I've done this, I can now see that my force is pointing to the right. My induced force is to the right. My force is this way, left to right. However, this is a trick in the question. This is saying what is the direction it was originally moved in. So this means that it's not going to be to the right, it's actually going to be moved to the left. Right to left. Why? If you remember, the induced EMF, negative. It is opposite to the change. So this is a tricky question. This is finding the induced EMF, which is the force, and this time it's asking you which way it was moved to cause this induced EMF. If I have an induced EMF going from left to right, like we just figured out, that means it was moved the other way. So that's a tricky one. I like it. Okay, so let's continue onwards. A bar magnet is moved towards a coil. Which of the following describes the induced current in the coil? So a bar magnet is coming towards the coil. What does that mean? So here is a coil of wire, very nice, and I have a magnet coming towards it. The magnetic field will be getting stronger. It doesn't matter if it's a north or the south, it doesn't really care. Let's just say it's a north. This is my attempt at drawing an N. I drew it backwards for some reason. Let's try again. North, coming in. This doesn't like it. It doesn't like the field getting stronger as it comes in. It doesn't like it. It wants to repel it. It says, no, stop, go back. So it's pointing outwards. It's trying to repel it. And funnily enough, it induces a north here and a south here, if you wanted to know that. But this is trying to push away. So in this case, it generates a field that repels the bar magnet. It is generating a magnetic field that is repelling the magnet to try and push it away. So that means this is the best answer over here. If the magnet was leaving, by the way, if the magnet was leaving, then you would say the coil doesn't like that change. It says, no, come back, please. So it tries to bring it back. It wants to attract the magnet back again. So depending on the question that you get. This is moving towards, getting stronger, it wants to repel. If it's moving away, getting weaker, it wants to attract. Very nice. Now we have this loop of wire lying inside this plane. Very good. What will induce a current? So if we want to induce a current, we can make a few changes. There's a few changes we can make. We know the current is dependent on the EMF over R. And I know the EMF is the negative N change of flux over time. Change of flux. The flux can be changed in a few ways. I can change the field, I can change the area in contact with the field, and I can even change the angle because the flux is BA cos theta. I can even change the speed, by the way, that I'm doing it in. So these are the things, the factors that will affect the current flowing through it. Okay, loop move to the right within the field. So if I take this loop and I move it within the same field, I am still inside the field. I haven't exited or entered the field. There is no change in flux, so that means nothing will be induced. This induces nothing. I am still within the field. I didn't change my angle, my area. I didn't change anything. I just moved around inside the field. Decreasing the strength of the field? Yes. Decreasing the field will decrease my EMF, thus decreasing my current. This is good. Rotating the loop about a horizontal axis basically means I'm flattening it. It's coming out towards me or in away from me. I am basically just changing my area. I rotate the loop, my angle. I change my angle. Yes, I will induce an EMF. So the angle will change. So this is good. 2 and 3 are the better answers. I will pick D. Very nice. Now we're moving on to a capacitor question. So a capacitor has 1 nanofarads connected to this voltage of 0.3 kilo. What is the charge on the plate? So remember nano means times 10 to the minus 9, nano 9. This is 0.3 kilo. Kilo means times 10 to the 3, positive 3. That simply means 300 volts. I don't know why they made it complicated. You need to find the charge on the plates. Q equals CV. That's all you need to do. I have C. I have 1 times 10 to the minus 9 multiplied by, I'll write it, 0.3 times 10 to the positive 3. That simply means 300. So putting this into my calculator, 1 times 10 to the minus 9 times 0.3 times 10 to the positive 3, I get 3 times 10 to the minus 7 coulombs. Great, but there's a problem now. I don't know what I'm supposed to choose over here. Is it 330, 300? Obviously it's not C. Which one is it? Well, there's a little trick. you can actually do this. If I want to put this into nanocoulombs, I know nano is 10 to the minus 9, so what I'll do is I'll divide this by 10 to the minus 9. To put it into nano, I can divide by 10 to the minus 9. If I did that directly, I get 300. That means I now have 300 nanocoulombs. So I have now solved this. I have got D. That's a little trick that you can use. If you want to convert it to the unit, just divide by that. That's nice. Okay. Now, parallel plate capacitor, constant EMF. I have locked in the voltage. The voltage is not going to change. So if there was an option here that asks for the voltage, the EMF, you would say unchanged. It does not change. So what's happening now? Changes the energy when we do what? I doubled the separation between the plates. So if you remember the formula, it's the epsilon naught A over D. If I double the distance between the plates, I will half the capacitance. It will reduce. The capacitance depends on the distance between the plates. So half, half, half. C is out. Very nice. Next, what happens to my charge? Well, we just did Q equals CV, didn't we? I reduced my capacitance. Voltage is locked. But I've reduced the capacitance. It means my charge will be reduced as well. So that means I have halved my charge. Very nice. Halved and halved. D is out. I have A or B to choose from. Energy stored. Well, energy is, there's a few formulas. Energy is the work or energy, whatever you want to choose. It's a half QV, a half CV squared and all that stuff. But the idea here is, well, we've changed the Q, we've decreased both of them, so it doesn't really matter then, does it? Because I've reduced my charge, which means I've reduced my energy stored. That's wrong. This one is correct, B. And it makes sense. If I have less capacitance, I can hold less charge. If I'm holding less charge, it means I have less energy stored because I have less charge. Makes sense. Very nice. Next, we're talking about this variation of charge with this on this capacitor. What is the capacitance? So you have a graph. You can just directly remember that graph. The slope of this, rise over run, will be my capacitance. This is my capacitance. You can verify that by doing rise over run, and you can see what the rise and the run is. The rise and the run. The rise is Q divided by V. Q over V, that is this formula rearranged. So you can just do Q over V. If you want to find the capacitance of this capacitor, just pick 2 points and do it. You can pick any 2 points you want, really. So we have this one here, Q over V. You can maybe even just do this one. It doesn't matter. If you notice, I've doubled this. This also doubled. So you'll get the same answer. So I can just do whatever I want, to be honest. 0.002 divided by 4. You're supposed to do x2 minus x1, y2 minus y1, all that rubbish, but I'm going to skip that just to save time. That's supposed to be a 2, by the way. By putting this into your calculator, hopefully you will get the answer of, what is this? 5 times 10 to the minus 4. Let me just double check that with another point. Yes, very good. I like it. Okay, charge stored by the capacitor at 16 volts. Charge stored at the capacitor at 16 volts. That's a strange one. It's asking for charge, however, all the answers are in joules. The charge at 16 volts, by the way, let me get rid of my writing over here. The charge at 16 volts is here. There. That is 0.008 coulombs. Obviously not an option. That makes me think this is a mistake in the question, and they probably wanted to ask for the energy stored. Energy, you can say, is a half QV, which again makes sense because this is a triangle shape, right? As this area under the graph is the energy stored. This is the area that I'm using, all of this area here. So to find that, let me erase all this stuff. To find the area under the graph is a half times the base times the height. A half QV, which is fine. A half multiplied by 0.008 multiplied by 16. And I wonder if I will get that answer in the answers. Let's check. 0.5 times 0.008 times 16. My answer is 0.064. Yes, it is 0.064 joules. So the question was asking for energy, actually. So it's a mistake in the question. A half QV, energy. Very nice. Okay, Next, we're moving on to some capacitors in parallel, and if you forgot the rules, there is a nice video I've made on this which talks about the rules for series in parallel. Long story short, voltage in parallel is the same. This voltage is given to each electron that lands on each of these capacitors. So the voltage is simply the same in all of them. The combined capacitance in the circuit is opposite of the resistors rule. If you remember, resistors in parallel was 1 over 1 over, and this one, you just simply add them. If you wanted to find the total capacitance, you can just add 20 plus 40 plus 60, 120. It's bigger than the biggest capacitor. That's another little way you can see. These are definitely going to be wrong. This is the only number that's bigger than the biggest capacitor. The total charge stored on the capacitors, charge, okay, no problem, equals Q equals CV. The total charge, I will use my total capacitance, 120 times 10 to the minus 9, multiplied by the voltage of 12. And if I put that into my calculator, let's see what I get. 120 times 10 to the minus 9 times that by 12, I get 1.44. 1.44 times 10 to the minus 6 coulombs. Now, I can see that micro is minus 6, but just to verify, if you remember, you can do division, divide by 10 to the minus 6. I just cancel it, really. That becomes 1.44 micro coulombs. I just wanted to show you another example of using that. This is a bit more straightforward. We have the answer anyway. I like it. All right, I'm going to pause that there. The video is going to get a bit long, and I'll start again in the next one. Thank you.